Poisson distribution. Poisson distribution is when we are counting the number of occurrences of an event in a given unit of time, distance, area, or volume. So this is a different color here. We are counting the number of occurrences of an event in a given unit of time, distance, area, or volume. So for example, we can count the number of car accidents in a day, number of car accidents in a day, or we can count the number of dandelions in a square meter plot of land. This number will be a random variable that may or may not have a Poisson distribution depending on the situation. So what are the situations? The situations are two, that events are occurring independently, and probability that event occurs in a given length of time does not change over time or time. So probability that event occurs in a given time or area, volume, distance, depending on the situation, does not change over time, area, volume, or distance. If these conditions hold, then the random variable has a Poisson distribution. And what is the PMF for Poisson distribution? That is probability of x is equal to little x is equal to lambda x e minus lambda divided by x factorial, and e is, or rather, 2.71828, and mean is lambda. So we can use the mean if the other formula, and the variance for Poisson distribution is also lambda. So for Poisson distribution, mean and variance are the same. So let's do an example. 1 nanogram of plutonium will have an average of 2.3 radioactive decays per second, and the number of decays will follow a Poisson distribution, which are two things, which are they are occurring independently and they are also not changing over time. What is the probability that in a 2-second period, so this is the question then, probability that in a 2-second period there are exactly 3 radioactive decays. So here we can see that the x, we have this formula, the x, which is the Poisson distribution variable or random variable, which is the number of decays in a 2-second period. Number of decays in a x is the number of decays and the small x is the 2-second. This is the small x. So lambda is equal to mu, which is what? So which is 2.3 times 2. And why is it times 2? The mean number of occurrence in the time period. So 1 second. So what is mu? So mean number of occurrences in the time period. So we want to know the mean number of occurrences in the time period. So in 1 second the mean is, so 2 second the mean occurrences is going to be 2.3 times 2, that is equal to 4.6. So probability of x is equal to 3 is going to be lambda x e to the power minus lambda upon x factorial. This is going to be 4.6 times 3 e to the power minus 4.6, which is minus lambda, and 3 factorial, which comes out to be 0.163. Now if we want to know that there are no more, so suppose the question is that no more than 3 radioactive decays, then what you will have to do is you will have to do the probability of 0, 1, 2 and 3 and then add them up. This is another concept, that binomial distribution tends towards Poisson distribution as n increases to infinity and probability reaches 0 and NP stays constant. Then binomial distribution approaches Poisson distribution, or Poisson distribution with lambda is equal to NP closely approximate the binomial distribution if n is very large and p is very small. But that is, n has to be very large and p has to be very small, then it will approximate. Now sometimes it's very difficult to determine the random variable from the Poisson distribution because the formula is complex, while the random variable with binomial distribution it is much more easier. So this information is very helpful in calculating some of the random variable PMFs.